everybody. Welcome to the lecture of ion separation. Last lecture, I talked about the mechanical method for the cell lysis, that is the homogenizer. But this lecture, we focus on the another type of homogenizer that we call Bismuth. This is the picture that describes the Bismuth side. Where we have a feed in this zone and output in this zone, and also we have the architecture and this side we rotate the architecture and feed to contact with the architecture with some breakage of the cell side. And small cell and suspension of small cell is out in this direction. So we architected. For this case, we can operate with batch operation or continuous operation. Right. We have the motor in this. Motor with to drive the shaft to rotate the architecture. The architecture. And also architecture contact with the cell that we saw that there are some break. And then the cell will release some liquid. And all of the component will move out in this direction and then feed in this direction. If we operate as continuous, it may be out and feed again, something more and feed again. If we operate with batch mode, only input in this, and then we move out only one time, something like this. This is the main part of the Bismuth. Okay. For the Bismuth, we can express like at the batch mode. We can use the equation to describe the operation of the batch mode value. Log 1 minus x equal to minus kt, where t is the time, batch time, batch time. What's the batch time? For this case, the time that the feed start from here and then, and finally is out of this. This is the batch time for his assignment. Okay, if it is operated with a continuous mode, the correlation can be described by this equation. It is for batch mode, and it is for continuous mode. It's 1 divided by 1 minus x equal to 1 plus kt divided j of this power j. K is a constant. K is a constant. Maybe it's derived or obtained from the experimental data. T for batch is the initial time until its final time. Initial or final time. For continuous process, for the process, the time is mean the resident time, the time that the cell stay in the reactor or stay in the equipment. That's that. And also we can determine the mean resident time by volume of liquid divided by the flow rate. That's that. If we know the volume of suspension of the liquid, we divide this by the flow rate. We will get the resident time for this case T. And J is the number of continuous tank reactor in series or need not be integer. But parameter J also is determined from the experiment method from the resident time distribution. So K and J is constant. K and J is constant. And also because it is operated by the batch mode. Operated by the batch mode. Okay. And also there are some generate the heat energy can generate during the operation. During operation. And the prediction of power consumption of this so-called crushing or grinding operation is created by Hicks law. Hicks law is based on the particle size reduction or Lichtinger law of grinding. With energy will be correlated to change the surface area. There are some people, some researchers suggest that what these laws are suitable for tissue grinding. For Hicks law or Hicks law can be applied for the tissue grinding, but not useful for modeling cell disruption. And instead, they suggest an equation for negative form. They suggest the form of the equation C divided by C max equal to 1 minus exponential minus T divided by zeta. And all this power n. See the concentration of product that released from the cell. Cmax is the maximum amount of concentration or maximum amount of product. That's right, of product in the cell. T is the time. As I say, that is the time constant, and then this number of parts through the device. That's right. For example, for n, it may be if we operate continuously, maybe some is one pass again, two pass, three pass, something like this. For example, okay. For example, I need to determine the ultrasonification of a cell suspension. A cell suspension had an intracellular antibiotic concentration of 10 milligram per milliliter. That means in the cell will contain 10 milligram per milliliter of antibiotic. After we dislodge or rupture the cell, so the maximum concentration that we can obtain from the cell is 10 milligram per milliliter. Okay, for the experimental data, at the end of 5 minutes of ultrasonification, 20% of the antibiotic is released. Okay, my question is, how long will it take to release 95% of the antibiotic? Okay, we have two conditions. The first condition will release 20%. The second condition will release 95%. That's right. For this case, we can apply this equation. For this equation, we know C is 20% for the first condition, and C is 95% of the second condition. That's right, second condition. Okay, C mean is the concentration of the released product, and C is the maximum concentration of the released product in the cell. That's right, in the cell. In the cell. Okay. For this case, at time 5 minutes, C 20% of antibiotic is released. That means from 10 milligram per milliliter, it released 20%. That means C equal to 0.2 multiplied by 10. It is C. It is C. And the maximum is 10 milligram per milliliter is Cmax. Right? For this case, time it should be converted into second. 5 minutes multiplied by 60, we get 300 seconds. That's right. And theta is constant. For this case, we assume n equal to 1 because we don't know it is how many parts. Okay, we assume it's only one part for that case. Okay, for one part, 0.2 multiplied 10 is C. That's right. It's amount of antibiotic release, 20%. 10 is maximum. Okay, and then for the experimental data at 20% release, we can calculate theta is a constant. Theta is constant for all the experiments. That's right, for all the percent release. Okay, for this we can solve for theta, and theta we get theta equal to 1,345 seconds. And then we know this, we can substitute it into this equation. That's right, and then you can calculate time for the second equation. How long? That's right. How long that we will take the 95% of antibiotic out of the cell. That's right, out of the cell. Okay, for this case, C is 0.95 multiplied by 10. This is the concentration that released. 10 is the maximum concentration. T is variable for this case, and this is the theta. And then you can solve for T. You get 4,028 seconds or 67 minutes for that case. Okay. This is the last slide that we talk about the cell disruption. Okay. As I talked to you, the cell disruption, we would like to separate the desired product that's included in the cell. That we talk about it is the intracellular product. For intracellular product, we have to separate cell out of the liquid first, and then we rupture the cell. And then cell will release desired product. And the next step, we have to separate that's right, the solid or the liquid that released from the cell. That's right. We can separate solid by centrifugation, by filtration, and the next step, we will focus on the liquid mixture. That's right. the liquid mixture is maybe solute dissolved in the liquid, solute dissolved the water. There are a lot of kind of components dissolved together with the solution. That's right. For the next, we maybe talk about the extraction, sorption, crystallization, something like this to separate the solute from the liquid, the desired product from the liquid. We will continue this for the next lecture. Okay, thank you for this lecture.